Hello. It's been a while since I posted anything to this channel, but I recently completed a project which I thought would be a good fit. The project is basically an implementation of the transformer model from this paper from 2017, Attention is All You Need. This was the paper that introduced the transformer model to the machine learning community. The transformer model has since gone on to become, in my opinion, far and away kind of the most impactful model, at least in terms of putting machine learning in the hands of end users. So it was initially known for getting outstanding results in text generation, so stuff like ChatGPT and other derivatives of that model now have become very popular for people's use in their everyday lives. Initially, this paper, the model was applied to the task of machine translation, and actually gave pretty well. Certainly, the improvement wouldn't be indicative of the huge impact it would have on the field. In the field of machine learning. We can see here they say that they have improved to 28.4 BLEU. This is a standardized scoring standard that's used in translation applications, and just improving by 2 points to get there. So good in the context of a paper, but certainly not giving any indication of the huge impact it would have on machine learning. Although I suppose if you're a machine learning expert and paying attention, it would be notable that such a new model would be getting state-of-the-art results just on this kind of like first implementation. Okay, so before looking at any code, I'd like to go through some of the figures that they give in this paper. This is the first figure, which sort of gives a visualization of the architecture of the model. Also, before we go any further, I should mention that I'm really going to be focusing on like transformer specific concepts here. So, and therefore I'm assuming a kind of an understanding of more general machine learning concepts, something like an input embedding, something like a feed forward network. If those terms are unfamiliar to you, you're probably better served engaging with some other content. But yeah, back to the transformer. Basically, the transformer can be categorized as an encoder-decoder model. And what that means is that there's sort of two halves of the model. The job of the encoder is to take a set of input information. In the case of machine translation, that is a set of words from our source language, and generate a contextual information, which is then used by our decoder in conjunction with any previous predictions, and use that to make a prediction, again, in the case of machine translation, into a word in our target language. So just to briefly go through a flow here, which is essentially what we'll be doing in the code walkthrough, we can talk, so the inputs here, and I'm just going to keep reusing the example of machine translation. That would be a set of words from our source language. When it's talking about an input embedding, so the way that these models work is that each word is represented to the model as an input embedding, an embedding meaning sort of a vector which gives a profile of the word. So to give just an intuitive understanding of that, this vector sort of carries the meaning of the word as it's seen to the model, and as a byproduct, similar words will have similar vectors. So there's this multi-head attention process that just means a parallelized dot product attention. I'm going to be talking about that process later, but the point of this positional encoding is that process does not kind of respect positional information. That's obviously very important in translation. So this positional encoding is applied, basically a unique vector on top of those existing input embedding vectors that gives positional information to the model. This multi-head attention process is then applied, a feed-forward network, so we have some learned layers, and that is one single encoder block, which can be repeated n times. This model is flexible in that sense. And then we have our sort of encoded information. The decoder is similar in that has a similar structure. So we have our output embeddings. Those are previous predictions. We sort of have a default previous prediction that's going in. That same multi-head attention process is applied, and then we get multi-head attention using the encoded information, and then we use that to make our final prediction. Next, I'm going to be looking at what this multi-head attention process actually is. Okay, so this figure contains two diagrams, one for scaled dot product attention and one for multi-head attention. Multi-head attention is really just parallelized scaled dot product attention, so that's what I'm going to be focusing on. And what that consists of is these operations. So we have three inputs. QKV stand for queries, keys, and values. So this is what's being shown here as well. Also, when I refer to self-attention, that means that each of those input values is actually the same tensor that's being inputted, performing attention on itself. So first we have this matrix multiplication here between the queries and the keys. So this value will actually be transposed, and you wind up with this square matrix, and it's often called the attention weights. And this was really the core innovation of this model. Basically, something that these sequence models often struggle with is retaining information over long sequences of text. And this is what this problem more or less solves, is any word within the sequence can be impacted equally by something as much as something, way back at the start of the sequence or something right next to it. It's sort of agnostic in terms of the distance. Any word within the sequence can impact it equally. And that's what the attention weights show. You can have these visual demonstrations of this, which I'll show later in this video. Scaling, masking happens in certain cases. Basically, each of the input sequences has to be of a certain length, but we have these padding tokens which indicate that no information is actually there, so that the mask can be applied in those circumstances. In something like where you're using sentences, if the sentence doesn't reach the max length allowed, then you should use masking. There are going to be some applications, say you're using images, then all of the image lengths might be uniform, and you wouldn't need to do this. We have soft maxing and then matrix multiplication, which lets us kind of return to the original dimensions that we had. Yeah, so one last thing that I would like to show here is they give this interesting diagram at the end, which shows kind of the effect of self-attention here. So we can see the way they've shown this is they have the same sequence here twice, and they are showing which words making is paying the most attention to, or most highly impacted the context vector that's eventually going to be generated here. So we can see that making is paying attention to itself, but what they are highlighting here is that they're highlighting the words more difficult. We see that it's paying more attention to those words and kind of ignoring a lot of the rest. And that's therefore the machine can see how the word making is being used, rather than just seeing sort of the words directly behind it or directly around it. So I think that's all I wanted to show from this paper. Next, I'll be looking at sort of how the data is organized in this project before going through the model. Okay, so this project uses the Europarl dataset. What that is basically this corpus of sentences in various European languages that were recorded in the European Union Parliament proceedings. And here, the model that I trained is translating from English to French. So that's what's contained in these files, is a set of English source phrases and the French targets that we're hoping to recreate using our model. So first off, I have a data file to sort of process this data. I think I mentioned earlier that we're not using the words as an input to our models. These are first being transformed via this process to vocabularies. Or we are creating vocabularies based on these files. What the vocabulary does is every unique word that appears within these corpuses. So we create a source vocabulary and a target vocabulary. So each English word is mapped to an index within the English vocabulary, likewise for the French vocabulary. And then those indexes are used by the model to map to an embedding. And so what the embedding is basically is a vector form of the word. And the vector sort of contains information about the word that can be used by the model, and that is used by the model to sort of generate this context and eventually generate the predictions. So that's kind of what I have here. Is I'm iterating through those files. I'm doing some data pruning here, just undesirable symbols that kind of like blow up the vocabulary. Also, one thing that I'm doing here, I think I mentioned earlier that the inputs for the transformer have to be uniform. So I chose a fairly short input length of basically, for it to be considered a valid entry, both the source and the target phrase have to be of length 16 words or fewer. And any sort of excess length, if it comes in below 16, is padded out with these special tokens. In fact, actually, that's something that we kind of see here is, I think, yes, we have this beginning of sentence token and an end of sentence token. So those indicate to the model where the beginning and end of the phrase are, and any sort of excess spaces that are not used by the sentence have what's a padding token padded within there to make sure that all of them, that every target and source entry have a uniform length. Also included here, so here I have my vocabulary classes, just basic operations to retrieve data from them, but I also have this sort of inverse data. This is used, I think, just on the target vocabulary. So at the end, our model spits out a predicted set of indexes, and we use this to actually get a human readable translation at the end of this. And then finally, I have this sort of Europol data class. This is what's finally using those vocabularies and feeding. I think that these are generators that actually feed the model. Okay. So I'd also like to kind of perform an overview of the model structure as it exists in the code base. It follows this diagram pretty closely, so I'll be referring to that throughout the process. But basically, each of the major components here is represented by a class within the code here. So you can see basically the top of our model would be this encoder decoder class, which includes the encoder and decoder being initialized, which are used in the initialization set in the initialization. And this forward function here, which is where we're getting our final predictions from. Basically, we have our encoder inputs represented here in the diagram, and decoder inputs represented here in the diagram. So that can either be in training the entire set of decoder predicted values, or when we're doing predictions, the predictions at that point in time. So our forward function here, we're using PyTorch for this. So we're using forward functions for each class to process information. We set our encoder input through the encoder. This is generating our sort of encoder context here, which is then fed into the decoder via this decoder state variable. And then those give our final prediction. So our encoder initialization, we have our hyperparameters coming in and setting various components of the encoder. So our embedding uses the vocabulary size and then the number of hiddens sort of gives model complexity. Basically, you get better performance with larger hidden layers, but it becomes more expensive in terms of the processing power required. The number of blocks is also set here. So we have this number of blocks and a sequential component, which gives us a sequence of blocks. So we have our input coming in here. Our inputs, these would be the word indexes. They are set to embeddings. The positional encoding is applied, and then they are set through those blocks sequentially. We get our X being generated from each block and set through, and then finally returned. So the block is so that basically follows exactly what we have inside this gray area. We have our multi-head attention being set, addition and normalization layer, a feed-forward network, additional and normalization layer once again. That's what's happening here in this forward function. Also, we get to see that this is a self-attention process. The self-attention, when we're calling it here, this is the query, the key, and the values inputs. It's the same value each time, making it a self-attention. A self-attention process. Here we have the decoder. It's a little more complex, but also similar in structure to the encoder. We're setting a similar set of parameters from our initial hyperparameters. And then for the forward, similarly, we are setting embeddings. There are two different paths here that it can take depending on whether it's predicting values from no known context, or if it's a fit or eval function where they are sort of processed all in parallelization. But basically, apart from that, it's very similar. We have the blocks being set in another sequential variable and that information being passed through and then eventually passed up. Also, the last thing I want to note here is this is where we sort of get the reverse process. We have this self-dense layer from our output. This is the output vocab size, and this is where our predictions are finally kind of being generated from that final context that's being pushed through this set of blocks. And then this block is fairly similar to the encoder block, except for the fact that it has two multi-head attention functions within it. One with that same, self-attention process. And here it's a little different. These key values, I think, carry the previous predictions, where the X only carries the latest prediction. Sorry, key values carry the entire set of latest predictions. So all existing predictions, whereas the X is only the latest prediction in that predict path, which I mentioned earlier. And then we have a similar second attention function here using that encoder context. And that is basically it. The last thing I like to go through here is these attention processes. So that is following these two figures here given in the paper. We have our multi-head attention here. So basically, we go in with our queries, keys, and values. We have these learnable layers that are applied to those, so we're not using just the raw embeddings that are put into our model, but instead we're introducing sort of more learnable layers to our model and performing the attention process on those. The attention is this dot product attention. So going through here, the queries, the keys, and the values go through the process that's outlined here. This has been broken up into heads. The keys are transposed. That sort of eliminates the hidden dimension layer, and we wind up with that square matrix of attention weights. That can then be masked either according to what information is available to the decoder at that time, or we might be masking according to the lengths of our sequence inputs. So if a sentence, basically we'd be masking the padded or end of sentence tokens that we shouldn't be paying, that we don't want our predictions to be paying attention to. Then we are returning to our sort of hidden weight dimension by performing the batch matrix multiplication process on that attention weights square and our value inputs here. At the end, then our results can then be concatenated to one another and then passed out and used back in our encoder or decoder blocks. Okay, so with that, I'm hoping that we have enough context to go into a code walkthrough or to step through the code and see how the data is handled by the model. I'm actually going to sort of deviate from my earlier practices of showing the training algorithms first, and I'm going to be showing predictions first. The reason for that is because I think the prediction is more intuitive, just the way that the decoder works when it's predicting rather than when it's training. Basically, when it's training, this process is parallelized, and it's training sort of each word based on previous predictions at once, which is confusing looking at it if you don't know what you're looking at. So I think we should go through this way and see how the predictions work based on the last predictions. So I'm just going to run this quick. We're looking at this eval sample process here, and basically what this is doing is it is loading a model. I've set a couple basic variables here. So I've set the batch size equal to 2, meaning that we're processing 2 sentences simultaneously. The model, so I have this model dictionary. Basically, this is the size of the model. I'm using the most simple model, which uses minimal. This is the length of the hidden layer, and then the blocks for the encoder and the decoder, and the number of heads is also 2. So these are going to make the data just a little it's going to make the data a little easier to follow as we go through. And what this does is it's pulling 2 English sentences from the evaluation set of data, and we can see here that this is the machine translation and the French translation. So even if it doesn't match it perfectly, we can see in one we actually did get a perfect translation, but in this one it's gone for something kind of far. Like, one thing about this data set is sometimes the translations sort of get rephrased, and the machine model will often produce a decent translation. So I think that that's the case. What happened here? Anyway, I'm going to start debugging and just explaining the data as we go through. So this is the prediction process here. Here we are putting our source and our source valid length variables into the encoder. So the encoder block, it's helpful to look at the shapes of these. We can see that our shape is 2 by 16 here. So what that means is those 2 sentences each are 16 sort of words long. And in fact the length is actually what's described by this source valid length. So we can see that both are of length 14. We can also see reflected here, we have at the end the same 3 numbers on both of them because they're both length 14. So this would be our end of sentence token and then 2 padding tokens. The rest of these represent words. I'm not sure if I said it earlier, only the decoder has the beginning of sentence token. It's not necessary in the encoder. Anyway, as I step through here, we are going to go into our encoder. And so basically what this consists of, we have an embedding layer. So we're translating our indexes into those embeddings that I mentioned earlier, and we're actually going to impose positional encoding upon them. So one consequence of this whole attention process is even though we see which words are impacting the output of a word most strongly, without this positional encoding, that information is there would be no positional information available in that process. So that's what's happening here. This is the positional encoding process. Basically what that is doing is it's imposing a unique vector on each onto those embeddings. So this is a visual representation of that. Basically, these are generated using alternating sine and cosine waves of decreasing frequency, and just imposes kind of unique information that can be learned by the model to distinguish what the first entry, second entry, all of those, ad infinitum. So that's what we have here. I'm going to turn off this breakpoint. We initialize these self-attention weights, and then we are ready to enter our encoding blocks. So we have 2 blocks here. Entering into the first one, so we have these normalization layers, but within that we have our self-attention layer. So we have our input X here. Our input X, just gonna double check this shape, but yeah, we have our 2 sentences, each 16 words long, and now with the embedding length of a 128. So here we are in the multi-head attention. So the multi-head attention, so we just have 2 heads here that we're going to be using. And that's what's being handled by this process. So we actually have these, something that I didn't mention about the attention process is we're actually using these kind of like learnable layers here. So our queries are processed. We perform matrix multiplication on each of the query key and value inputs before this transposition takes place. Basically what we're doing here is we are, for that hidden layer, we are taking out the number of heads. We are essentially breaking that up evenly according to how many heads there are. In this case, that there's 2. So if our initial length was 128, we will wind up with a hidden with 2 heads, each of length 64. So that's what's happening here with these permutations. We can see the heads are getting taken out, and then they're being put to the front. That's happening in this permutation, and then those are being squished together. So we're going to wind up with, I think it should be 4 by 16 by 64. And similarly, a similar process for the keys and values. We're using a different layer for each of those, but it is the same, in this case, the same input, and therefore the same dimensions on the output. So our valid lengths here, we have 14 and 14. So both sentences, unfortunately, this is going to be a little more unclear because they're both of the same length. In fact, I might stop it here and run this again just so we have different lengths to make it a little more clear. Okay, so I ran the debugger again, and now we have 2 input sequences of differing lengths, 8 and 15. What we're going to do before entering the self-attention process is repeat each of those values to match the number of heads that the model has. In this case, we have 2 heads, so each value is repeated once. Then we enter our self-attention here, and we begin the process that we saw in that diagram on the initial paper. We're using torch batch matrix multiplication, multiplying the queries against the keys. So if we do queries.shape and keys.shape, first off, we can see that the number of the hidden dimension has been halved because there are 2 heads. So that's how that factor is treated. And we can see that the keys are being transposed. So that's what lets the batch matrix multiplication be valid. That 64 is going to disappear once we have our scores. And the scores here, let's take a quick look at that. We wind up with, 4 by 16 by 16. So the 4 is, we have our initial 2 sequence inputs, and then for each of those by 2 heads. 16 would be the sequence length, and then each sequence length we have a score which determines just kind of the impact of that word on the initial word of that sequence, where the name self-attention comes from. So basically, we are finding the words that most have that determine the meaning of that word. Here we also go through the masking process. So because we want to be discarding any impact coming from the padding tokens, so that's for any words after the index 8 in the first sequence, we want to get rid of. To do that, we are putting our scores matrix and our valid lens variable into this masked softmax process. There's a couple different paths here, but the encoder always goes through here. Once again, we are going to be repeating values, this time 16 times. So we're going to wind up with this valid length variable of length 64, lens dot shape, and that is going to be part of our input into this masking process. What we're doing here is we're using the arange function. The arange function generates an ascending sequence, and for each of those, we're using this against our valid lengths of length 64 to come up with this mask variable. So the mask shape is 64 by 16, and if we look at some of the values in it, we can see here it is setting true to any values over the index of 8 for the first one, and in the last one, because it's length 15, we are only setting that last value to true. Just to make it a little more clear. And then each of those, so we are applying the mask to X, and where mask is true, we are setting that to this very low value that we have. Basically, so the score gets essentially discarded when we have our softmax process, which is what's happening right here. We're going back to our original shape of 4 by 16 by 16 and performing the softmax on that. At this point, we actually can show that diagram that I mentioned earlier, the attention weights matrix. So this is for the first head. So we can see that our first word is paying complete attention. This is a heat mapping. So basically the black means that it's is a value of 0 or close to 0. You can see in the bottom right of this window. And then up there, it goes all the way up to 1. Similarly, for the second word, it is paying attention to this word. And then after one thing to note here is also it will never pay attention to any of the words after that we've discarded in our mask. That was the entire point of that process. So we can see that there's a cutoff here. Just to look at another one. So let's look at, say, the second. So this is the first head of the second sequence, and it because there are 15. Or was it 15 or 16 values in play? 15 values in play. It sort of goes all the way to the end here, and any of those words can be targeted and sort of considered when determining sort of the actual meaning of this word. So with that, we are actually through the thick of it. That was our attention process. Our transpose output is basically the reverse process of this transposition that we had. We are going to take the number of heads back out from here, do a reverse permutation. So now the number of heads has been sent to the back and then kind of squished together here. And then we have one final linear transformation to that output concat. So let's just take a look at that. Concat.shape. And we have our, our two sequences, each of length 16, now with this 128 sort of context, hidden dimension context attached to it. So now we are exiting our encoder block. We have this additive normalization. So this is like that residual layer. And then normalization being attached to one another, and then this feed forward network, which I think is just two linear transformations, and that is our block. That process is repeated once more. was hoping not to hit these. So here we are in the encoder. So that block is repeated once more in the small model dictionary for the 2 blocks. And with that, we are through our encoder. So I'll take a break here, and then I'll go through the prediction process for the encoder. Okay, so we are through the encoder. We have our encoder outputs here. And now we're going to begin the decoding stage of the transformer prediction process. So just to recap, our encoder has brought us this contextual information. So we have our 2 sequences, each of length 16, and now carrying these sort of like context vectors with the hidden dimension 128. We are going to initialize a decoder state. So using that, plus using the valid lengths of the encoder context, and because we're going to be using that for another a dot product attention process within the decoder. So just going in here, we're making a simple list of the encoder outputs, the valid lengths, and then also these this list of none objects, which is eventually going to be populated with sort of our predicted values that we'll be predicting iteratively using the decoder. So that's our state, attention weights, and then this is the beginning of our output vectors right here. So for the outputs, we are first creating this vector filled with BOS tokens. So what that means, BOS is the special token meaning beginning of sentence. So every sentence is going to start with that. This is telling our, because we need some value to give to our decoder for the initial attention processes, this value just kind of says, hey, this is the beginning of the sentence. We haven't actually generated any predictions yet. So we're going to be repeating this target max length times, as I said before, these sequence lengths are 16. So we're going to be running through this loop 16 times, each time generating a predicted word and using that for the next prediction. So self-decoder going in with the last elements of our outputs, which is our BOS token and our decoder state, which I described earlier. Here we have a similar process, just more position encoding and making our attention weights for the decoder. Because we are in predict mode, we aren't doing any masking on where every time we're considering all of our predicted tokens that we've made so far. So we enter our block. We're saving some of the state information to variables. And we are setting our key values for the first time. These key values are getting saved to those state blocks that I mentioned earlier. So yeah, those none objects are now populated, or at least for the first block, and we enter our self-attention process. In this case, it's the BOS tokens in this process going against themselves, so there's not much information to be gleaned from it, but as we get predictions, we can start to see which of the previous predicted words become more important on subsequent predictions. So in this one, we just do a simple softmax. There's no masking occurring, and we wind up with this very simple looking attention weight output object, which is just it's one index. So our BOS token looking against the other BOS token. So that is our first iteration. And then this, so now we have our Y object, and this is actually going to be, sorry, why not shape? And we're going to be comparing this against our encoder outputs, performing a self-attention process there. So in this case, our queries is the set of vectors representing our sort of decoder prediction path, and then these keys and values are both coming from the from our finished encoder values. Those are going to stay static throughout the process. So once again, yeah, we are doing this valid length repeat interleave technique. I think that is going to go the exact same way that it did before. Yeah, once again, this is going to be that vector of length 64. We go in and we're taking out those sort of invalid padding, the invalid values from the encoder, the ones that represent the padding tokens. And that is going to take us through our first block. So yeah, each block of the decoder has these two attention operations within it. And okay, so I'm going to just skip this process on the second run through. Apparently not. And we are coming out with our first prediction here. So we come up with this y vector. So y dot shape in this case. So 2 by 1 by 47,173. So that's the word dimension of our target vocabulary. Our argmax is being performed there. So basically this is a set of predictions. So if we do, y 0, 0, we wind up with this very long vector of, and basically the largest value there will be our prediction. So we append that to our outputs, and now our outputs has that bit more context on it. So we have this these two BOS tokens, and then followed by this column of predicted words. This process is going to repeat, like I said, 16 times. I think I will jump ahead a bit until we have a set of predictions and we can see what that first attention block looks like once we've built a few word predictions. Okay, so I've jumped ahead with two different predictions, and I'm on the 10th iteration of this loop, meaning that we've made 10 predictions in addition to the first BOS token predictions. So our output has more words, or our outputs have more words to look at, and hopefully get a more interesting attention matrix. So I'm just going to step through here. We're into the decoder. I think this is the exact same process that we saw before. This block is going to look slightly different because we have established a state here. This state is keeping track of the previous predictions. We are adding the latest prediction, which is our x, our x input, and we are appending that to the previous predictions. Then we're performing our self-attention, so it's that x input against all existing inputs. Our valid lengths here is none, so we have the same transformations and transpositions that we saw before, and this process becomes a little easier here because the masked softmax is unnecessary. We just have a straight softmax. We aren't ignoring any, doing any logic involving valid lengths or anything like that. So yeah, a lot of these turn out kind of like disappointingly simple. You can see that this latest prediction is only looking at this 7 index. I'll go through these and just see if once in a while one will be considering multiple words. But yeah, that's sort of the logic behind these heads. But behind multiple heads here is that the multiple heads might pick up different sort of relations, basically just different types of logic that the model might use to try and figure out which words are impacting the current prediction in different ways. Anyway, so that's what we got out of that, just single words being considered. on the latest prediction, we have this process to fix our dimensions, and we can repeat the process here. This actually looks the exact same as we did before. So I might just skip ahead to our final output, actually, and we can see our final predictions. Okay, so I've set the debug point here. We are just going to skip ahead, and now we have our full outputs sort of list. Yeah, you can see that it ends with these 802s and these 803s, so those would be the end of sentence and the padding tokens, respectively. And we are so slicing that, starting from the first one, we're just ignoring those initial BOS tokens and concatenating along the first dimension to get us a set of our set of predictions. Here we are just going through and for each set. So I think that I have, what is it, source, translation, and predictions that are coming out here. Some of those are, so two of those are generated by this like data generator object. So that would be like the target and the source, and then we have our predictions. For each of those, we're just going to be using the source vocab and the target vocab for the target and our predicted translations, and we're going to see how close we got. So I think I can just press play here, and in our terminal we finally get our two outputs. Okay, so the last thing I want to show here is the sort of decoder training process and how it differs from the decoder prediction process. The encoder process, I should say, is the same. Here we are running this fit function, so we're doing the training rather than this eval sample prediction function that we were running before. I think I mentioned earlier, but the decoder training function takes advantage of parallelization. So with the prediction, we only ever had access to the previously generated predictions, and our input was just our latest prediction. In this case, if we look at x.shape, so instead of it being 2 by 1 by 128, just representing our latest prediction, it's actually 16 by 128. So we are going through with the entire sequence length at once. And the reason we can do this is because we already have all of the data for this, and our target for each set for each element in that is the next element. So I'll show what that looks like on the end when we finally do our loss function. But for now, I'll just show how the logic here works as well. It sort of starts with this arange variable, which we're going to be building here instead of previously for the encoder, we would have had, an integer for each batch element. Here we have this kind of arange vector for every batch element. Other than that, it looks, I think, just about the same until we get into the self-attention part. We're going to be repeating those once again for the heads, so we wind up with, in this case, 4 arange vectors, and we enter our self-attention here. Our queries against the keys. So again, the query is the full set of predictions, and our keys will be the same size. Keys.shape. But we are going to be using our mask here again. Using those arange vectors. So this is sort of the secret sauce here. We're taking this path. We are not repeating anymore. We already have those, in this case, 64 elements that we're using. So if we go in here, our valid lens is sort of a column of 64 4 ascending sets of 16. And here we are going to be using that arange like we had before. And anyway, the effect of this, it's kind of a nasty looking line of Python, especially using these A ranges. But what it's giving us is 4 sets of triangular masked matrices, you could call them. So here are the first, looking at the first row, there's this one false value, and the rest will be set to true. Just as a reminder, the true means that it's going to be zeroed in the attention matrix. The next row has those 2 false values, which means that they're left alone, then so on and so forth until you have that set of 16 false, and then that process repeats 4 times. So what that looks like coming out the other end, we wind up with this attention matrix, so the 16 by 16 matrix. And one of the rules here is like all of the top right is getting discarded. You're only ever considering words that are available at the time that that word was passed through. So what that means, so this 0 represents the BOS token, and only the BOS token was available at that time. But then once we got to our first prediction has, you know, those 2 tokens available to it, then 3, then 4, then so on. Usually they wind up with this kind of like vertical line here, as you expect that that's when we start predicting just the padding tokens again and again. And it's only ever looking at that EOS token after that. So that is the basic logic there. I'd like to, so yeah, I'm just going to, the encoding process, I don't think we need to go through. I just wanted to take a look at the loss now. Okay, so picking up from that process, after we have gone through the blocks in our decoder, we wind up with this dense layer, and this dense layer is the one that finally gives us this linear transformation that gives us our output vocab size. So our X, I believe, just still has, yeah, our hidden dimension shape after going through our dense layer. And this is our final output. We actually arrive at our loss function. So our Y here, yeah, we have our 2 batch size, 16 word predictions, and then the word space is our target vocabulary word space, and that's going through our loss here. This is to get these in the right shape, and we use I think cross entropy is the one where we have a single target value. Just looking at, yeah, it's a Y dot shape is, yeah, a set of 32, so that would have been 2 by 16 before, representing the 16 values for the 2 batches. I'll just take a look at the values there. And yeah, we can sort of see, so each of these would represent words. And then we get to our EOS and BOS tokens. And then that process would start again for the last 16. I think that the last thing that I want to show here, so yeah, we go in with what this data object looks like. Yeah, so we have the data object, the input to the model here is our source tensor. So our source tensor is those indexes, the set of indexes that represent, in this case, the English source language words. We have target tensor at t-1. That is the one that uses those BOS tokens at the start. That one will always be ending with 1 padding token to compensate for the fact that the target tensor is those very same values, but advanced 1-time value. So just to look at that, data 1 and then data 3. We can see that each of these starts with 801, whereas each of these skips past that value. Yeah, hopefully I made that clear, is because for every instance, when we have our BOS token, we are looking to predict this very next token, and so on and so forth. Like all of these tokens are basically matching and should arise out of one another. so we can use that same source data all in one shot. Okay, so I think that's everything I wanted to cover in the code walkthrough portion on this topic. I hope that it was helpful for any of you guys who are learning to learn more about transformers or how they can be programmed. One thing I also want to mention is I expanded this project a little bit. I have this vision transformer. So this is a transformer applied to the problem of like image classification. We have categories of images, and it's actually a smaller model and quite a bit simpler, especially if you've gone through and understand all of the concepts within the base model that we just went through. So look out for that. Also want to say I'll be posting the source code in the description to this video, and I'll be hanging around in the comments if you guys want to ask any questions. Thanks for watching.